Alright, we're going to do matrices now, and we're going to do a 2 by 2 matrix. So what is a matrix? A matrix is a rectangular array of numbers, letter, whatever. It's just set in such a way, where you have it bracket off, and you have a set of number in rows and a set of number in columns, and it is represented by a capital letter. Alright, now the first thing you need to know about matrix is the order of a matrix. The order of a matrix is the amount of rows times or multiplied the amount of columns. And if you look at this matrix A here, it has two rows. Rows means across, horizontal, columns means vertical. And it also has two columns. So the order of this matrix is a 2 by 2. It's a 2 by 2 matrix, 2 rows times 2 columns. So let's come down here and you see order, rows times column, 2 by 2. And you also have this one here, same one at the top, 2 by 2. Let's try to get the order of these matrix here. And well, look at this one here. It has how many rows? Because we start with rows and column. 1, 2, 3 rows. So it's a 3-row matrix. And how many columns? 1, 2, 3, 4. 4 columns. So that's the matrix is a 3 by 4 matrix. What about this one here? How many rows? You see, actually 2 rows. You see 1, 2. Horizontally there is 2. So it's a 2 and there's 1 column. This one here, 1 row, 1 row, 1 row and 2 columns. Here you have 1, 2, 3 rows and 1, 2, 3 columns. So that's a 3 by 3 matrix. Coming over here, so we go quickly into addition and subtraction of matrices. Now, first thing you must note, matrix with different orders cannot be added. Let me say it again. Matrix or matrices with different orders cannot be added. So we want to get an illustration here. And how do we add them? We add matrices by adding the corresponding elements. So let's look at elements. This here, this letter A here, that letter is the first element in the first row. If you notice, let me see if I can adjust this camera a little bit. Good, that should be better. And let me see if I can enter some more light. Okay, good. Now, this A here is the first element in the first row and the first column. This B is the second element in the first row, but the first element in the first column, and so on. So we want to add A, B, C, D, and with B is equal to E, F, G, and we want to add that and see what it looks like. So this would be A plus B is A plus E, because they're in the same position. If you notice, A plus E, because they're in the same position. And then you have, give me another second. Okay, then you will have B plus F. B plus F, they're in the same position again. B plus F. Then C plus G. C plus G, same position. Then D plus H, same position. So that way we can add these numbers. So that's the result of this. Now, there is also, in everything you do, there is an identity when it comes to multiplication, division, and so on. And this is the additive identity matrix. If you add 0, if you subtract 2 from 2, you'll get 0, which is the identity. And if you add 2 to 0, you'll get back 2, again, which is the identity. So a matrix minus the same matrix will give you the identity matrix. Good. And this terminology, A minus B is not equal to B minus A. That means if you switch around the matrices, they will not be equal to the results will not be the same. So you're saying that it's not associative. So here you have a few examples, and I'm gonna work these examples, and then we go on to scalar multiplication. So we're adding A plus B. This would be A is 5 minus 7, 8, 3 plus b is minus 2, 4, minus 1, 3. Awesome. Coming down to the bottom, 5 plus minus 2. Remember, there's a plus in the middle there. Sorry, there's a plus supposed to be in the middle there. So 5 plus minus 2. So it's 5 plus minus 2. And minus 7 plus 4. Positions. Then 8 plus minus 1. And 3 plus 3. This will give you 5 plus minus 2 is 5 minus 2, which is 3. 7 plus minus 7 plus 4 is minus 3. This here will give us 7, and this one will give us 6. So this is our result when we add these matrices. Now the next one is a plus b plus c. We already know what a plus b is, so all we need to do is add this result to c. So a plus b bracket plus c is equal to this result here. Let me fix this here, which is 3 minus 3, 7, 6, plus c, which is 1, 0, minus 1, 2. Good. And now we're adding the same thing, positions. It will be 3 plus 1, and 7 plus minus 1, and minus 3 plus 0, and 6 plus 2. Good. Now we subtract. We have 4 here, minus 3 here, minus 6 here, and 8. So that's your answer. That's how we add and subtract matrices. Now if there was a let me go back here for me. If there was a subtraction between these two, like let me say it was a minus 1, 0, minus 1, 2. If there was a minus there, then it would have been let me do the minus one. Let me just separate them here and put the result here. 3 minus 2, 3. We have 7 and 6. Now we have to subtract. This would be 3 minus 1, minus 3 minus 0, 7 minus minus 1, and 6 minus 2. So the minus comes instead of the addition here. So this would be 2, and this would be minus 3 still. This would be 8. Minus and minus gives you a positive, and then yeah, you know what happens there. And this becomes 4. So that's it. Next topic, scalar multiplication. Now this is simple. If you have a number outside of the matrix, that number outside multiplies every element in the matrix. K times A, K times B, K times C, K times D. Every single element in the matrix is multiplied by that number. So let's do a quick example. Alright, so we have this P equal into that, Q equal to that, and we want half P plus 4 1/4 or quarter Q. So let's see. It becomes half of 6, 5 minus 2, 4, and 4 minus a quarter of 2, 0, 1, 8. So the half comes in and multiplies everything. So it's half of 6, which is, let me just put the answer because we know what it is. Half of 6 is 3, and half of 5 is 2 over 5, which is 2.5, but I'm going to use a fraction. Half of minus 2 is minus 1, and half of 4 is 2. And this will be minus 2 over 4, which is a half, we know that. So it's 1 over 2. Then this should still be 0, and this will still be 1 over 4 here when it comes in, and 8 divided by 4 is 2. So when you had your, and when you, because we have to subtract, right? We have to subtract. So this will be 3 minus a half minus 1 minus a quarter, and 5 over 2 minus 0, and 2 minus 2. 3 minus a half is 2.5. Just giving the answers here. 1 minus a quarter is actually 1 and a quarter. Well, yes, minus 1 and a quarter, which is 5 over 4. And this would be 0, and here would be 5 over 2. So that's our answer. That's how you do the scalar multiplication thing. Alright, we're after 10 minutes and we want to do matrix multiplication. So let's get this done. Alright, how do we know if a matrix can be multiplied or not? Show you many ways. It has to do with the order of the matrix. These are 2 by 2 matrix. Okay, so we know they can be multiplied. Look at this thing here. When you set down the matrix side by side, if this would be row times column. If the column of the first matrix and the row of the second matrix are equal, they can be multiplied. It says that they're compatible for multiplication. But if these two numbers in here are the same, then it can be multiplied. And if these two numbers, the two numbers outside will tell you what the result is. So I'm going to put down a few matrix and right up here, and you can tell me whether they can be multiplied or not. But we're basically dealing with 2 by 2 matrix. So here we go. What about this matrix here? Let's say 2, 1, 3, 4, 5, 7. What about that matrix there? And you're multiplying. This order is 2 by 3, right? And you're multiplying this matrix here. Let's see, 1, 2, 3, 4, 5. Let's put something here. 7, 6, 3, 1. And this is a 3 by 3. This matrix be the orders are different. We see that this is a 2 by 3, this is a 3 by 3. Can they be multiplied? Yes. Why? Because these two are the same number, and these two at the end will tell you what the result is. So that is how you know. But let me give you one more quickly. 1, 2, and what is this? This is a 2 by 1, and then we have 1, 2, 3, 4. Good. Can these be multiplied? 2 by 1, and this is a 2 by 2. Can they be multiplied? No. Why not? These are different. Okay? Alright. Let's do multiplication of 2 by 2 matrix. And this is how you multiply. You multiplying the rows. The rows of this matrix times the column of this one. Whichever one is in front. Let's put them side by side. 2, 3, minus 5, 4. We're multiplying that against minus 5, 1, 0, 2. Now, this is what I call the row matrix, and this is the column matrix. We're using the rows to multiply here. We're using columns to multiply here. And we multiply rows times column. Rows times column. Let's do the example quickly. So what is the row? This is the first row. It is 2 and 3 in the first row. And in the first column is minus 5 and 0 because column is downwards. So this would be 2 times minus 5 plus first times the first element in the first row times the first element in the first column, plus 3 times 0, the second element in the first row times the second element in the column. So it's first element in the row times the first element in the column, and the second element in the row times the second element in the column. That's how it works. Let's come across. It will be 2 times 1 plus 3 times 2. 2 times 1 plus 2 times 1 plus 3 times 2. Row times column. To the bottom, minus 5 times minus 5 plus 4 times 0. Row, column. And across here, minus 5 times 1 plus 4 times 2. And let's see what our answer is. This will be minus 10 plus 0. 3 times 0 is 0. This will be 2 plus 6. At the bottom here, minus 5 times minus 5 is 25 plus 0. 4 times 0. This will be minus 5 plus 8. And we just add or subtract. This would be minus 10. This would be 8. Minus 10, 8. 25. And this would be 3. And that is our answer. You can go ahead and try multiplying b times a and then a square times a. A square is a times a. So you're multiplying this a twice. And you can see what your answer is. Now that you know how to multiply. Let's deal with the determinant of a 2 by 2 matrix. Now, the determinant of a 2 by 2 matrix will tell you whether the matrix is singular or non-singular. Let me tell you what that means. if the determinant of the matrix is equal to 0, then the matrix is singular. But if the determinant is not equal to 0, if it's equal to some number, whether negative or positive, then the matrix is non-singular. Okay? So, how do we find the matrix or the determinant of a 2 by 2 matrix? This is what you call diagonal. Let me draw this little square here. We said a matrix is a rectangular array of numbers. So, let's use this little rectangle. It looks more like a rectangle. This is the leading diagonal from here to there. And this here is the non-leading diagonal. So, the determinant of a 2 by 2 matrix is the product of the leading diagonal subtract the product of the non-leading diagonal. So let's get that done. So what about this? So it will be, in this diagonal is A and D. So it's A times D minus the non-leading diagonal is B and C. That's what it is. So let's get the it's represented by the modulus of the capital letter, and this is equal to, this will be 3 times 4 minus 1 times 2, which is 12, minus 2, which equals to 10. This proves that this matrix is a non-singular matrix because its determinant is not equal to 0. So the depth of B now, the depth of B is equal to AD, the leading diagonal, times the non-leading diagonal BC. You should put back this formula here, which will be minus 2 times minus 3 minus 5 times 1, and minus 2 times, this is positive 6 minus 5, and our answer here is equal to 1. So again, this is a non-singular matrix. You can solve for C, that's not difficult. Let's deal with adjoint. And this is important, the adjoint of a 2 by 2 matrix. The adjoint of a 2 by 2 matrix is you have to switch the elements of the leading diagonal. So you have A and D here. You have to switch the elements of the leading diagonal and change the sign of the elements in the non-leading diagonal. We're going to find the adjoint for these matrices up here just now. So that would be the adjoint of this matrix A will be D, A, and minus C and minus B. We switch the position of the elements in the leading diagonal and we change the sign of the elements in the non-leading diagonal. So let me write back what A was up here. A was equal to 3, 2, 1, 4. B was equal to minus 2, 5, and let's put minus 1 here instead of 1, and minus 3. Let me just put positive, leave that positive 3, good. So we need to find the adjoint of these. So A adjoint ADG, this will equal to, we have to switch the position, so 4 comes here and 3 comes there, and we have to change the sign. It becomes minus 1 and minus 2. Simple as that. And now B adjoint, this is equal to, what happens? The 3 goes here and the minus 2 comes to the bottom. This becomes minus 5 and this becomes positive 1. And that's the adjoint. Now, inverse. Looks like I'm going fast because, well, you can go back and check these things and, make sure you get the understanding. Good. So inverse. Inverse of a 2 by 2 matrix. The inverse of a 2 by 2 matrix is equal to the 1 over the determinant times the adjoint. Everything that we just did. 1 over the determinant times the adjoint. So I'm going to find the inverse of one of these and you can do the others. And then, I'm going to show you another piece of understanding at the bottom here. But let me find the inverse of this one. So let's find we have to find the determinant first, because it's 1 over the determinant times the adjoint. So we have to find the determinant first. And the determinant is, it will be, let me put AD minus BC. Alright? And that will be 2 times 5 minus 1 times 3. This will be 10 minus 3, which is equal to 7. Good. Then the adjoint of A now, A adjoint. This is equal to, switch the elements of those in the leading diagonal. So 5 comes here, 2 goes there, and minus 1 and minus 3. So that's the inverse. So that's the adjoint. So let's get the inverse. The inverse is A inverse, represented like that, is 1 over 7, the determinant. times the adjoint. 5, 2, minus 1, minus 3. And that's it. And we need, this is critical for what we're going to do next. So now, if you multiply, and you can check it, if you multiply some inverse times the original matrix, you will get the identity matrix, the multiplicative identity matrix, and that will equal to 1, 0, 0, 1. Multiply this, the inverse here, times the matrix there, and tell me if you get this. So, moving on. We're supposed to go to vectors next, but before that, I'm going to do one example of simultaneous equations using the matrix method. So, let's get going. And this will be our final question for the morning, for now, and then we'll do the vectors later on in the next video. So, let's get this done. First thing we do when we're solving matrices using the matrix method is that we formulate matrices, because this is just plain linear equations. So we need to formulate matrices. So let's do that. With the positions of these elements, where they are in the pairs here, you leave it just like that. 4 was there, 5 was there, 3 and 2, and then we use x and y, our variables, and this is equal to minus 6 and 7. Nothing difficult about that, if you notice. We just formulate matrices using the position of these elements, x and y, at the top there. That's the only difference. Okay, so let's label them. Let's call this A, let's call this x, and let's call this B. Now, obviously, we're trying to find x and y in this matrix. So if we add a simple equation like this, ax equal b, if we want to find what x and y is, x is, we need to take over the a, and it becomes a inverse b. So in order to find the value for x and y, we need to find a inverse and multiply a inverse times b. So let me find a inverse quickly. I'm going to do that to the side. I'm going to find a inverse here. So a is the vector with the matrices, the matrix 4, minus 5, 3, and 2. So first, to find the inverse, we need the depth of A. This is A. So the depth of A, let me do it at the bottom A. The depth of A is equal to 4 times 2 minus 3 times minus 5. Good. So this will be 8 minus, this is a minus 15. It will be 8 plus 15, which equals to 23. 8 plus 15 equals, so we got that. Then we need the adjoint. I'm doing it separately because it will look jumbled up if we do it here. So I'm going to do it here separately. So we need the adjoint now. A adjoint. And this is equal to 2 comes here, 4 goes there. This changed to minus 3 and this changed to positive 5. So that's the adjoint. So the inverse of A is equal to 1 over 23 times 2, 5 minus 3, 4. Good. That's the inverse. Let's come back here now. So x and y is equal to A inverse B, and A inverse is 1 over 23, which 2, 5 minus 3, 4. 1 over 23 times minus 6 and 7. This is A inverse, just like that, A inverse times B, because we found it here, so we know what it is. And let's multiply here, and this will equal to 2 times 6, 1 over 23. Row is 2 times minus 6, and column 5 times plus 5 times 7. To the bottom, minus 3 times minus 6 plus 4 times 7. Good. So this is 1 over 23, not bringing in this scalar quantity as yet. And 2 times minus 6 is minus 12, plus this will be 35, and this will be plus 18, yeah, plus 18, minus 3 times minus 6 positive, plus this is 28, 28, 4 sevens are 28, 4, 6, 20, yeah, 28, I'm correct. And Now we need to add or subtract them, and we know that this here is 1 over 23. This will be 23. 35 minus 12 will give you 23. And 28 plus 18 gives you 46. And now you can bring in the scalar quantity. So this becomes 23 over 23 and 46 over 23. Well, we know this x and y now will equal to 1 and 2. So that's the value of x and y, 1 and 2. And that's how you solve simultaneous equation using the matrix method. So next topic, vector.